Now, in order to have a good discussion about kind of the classification of bonds, one of the things that you have to have a good understanding for is this concept known as electronegativity. And what electronegativity is a measure of basically how much a given atom wants electrons that are within a bond. Okay, so just to put things into perspective, we've got kind of a spectrum. So this is your periodic table, or the vast majority of your periodic table laid out. And where I've just drawn a little star is the element known as cesium. Cesium, Cs, is a metal. It is the least electronegative. A negative atom. And what that means is that cesium, basically whenever it is in a bond with another element, it's going to give up an electron. It's more likely, it wants that electron less than the other atom. Okay. The opposite end of the spectrum, which I'm going to switch colors for that up here, fluorine, F is the most electronegative. And what that means is that fluorine wants electrons within a bond. So if we had something like, let's say CF4, that's a molecule, and the central atom of that molecule is carbon, and this molecule looks a little bit like this. Now, if we think about this in terms of classification, well, that carbon is a nonmetal, fluorine is also a nonmetal. Now, electronegativity tells us, or this table of electronegativity tells us that fluorine wants the electrons within this bond. So these electrons that I'm circling right now, fluorine wants those electrons a lot more than something like carbon. Okay. Now, we'll get into calculating this in just a little bit, but kind of think about it in terms of even whenever you have sharing of an electron or sharing of electrons between two elements, it's not perfectly even. Okay, so that gives us the classification for a covalent bond as being a polar covalent bond. A polar covalent bond is the uneven sharing of electrons. Electrons spend more time around one of the atoms than the other. So if we take something like F2, well, F2 is a perfectly polar or perfectly covalent bond because they're both fluorine atoms. So these fluorine nuclei, they're going to share those electrons completely evenly because it's not like one fluorine wants the electrons more. Our next example, actually our next two examples, HF and LIF. Okay, those are both examples of pairing up fluorine, something very electronegative, with something else that's quite a bit less electronegative. And what we've got is basically these electrons occupying, well, more space around one of those nuclei. And so I visualize this as we've got the lithium right there and the fluorine, I'm sorry, my head's kind of obscuring it, right there. And so most of those electrons are going to be occupying that space around fluorine more so than lithium. Now, electronegativity is the ability of an atom in a molecule to attract electrons to itself. So if we use something like HCl as an example, chlorine is going to be partially negative charged, hence this delta negative symbol that we're using there. Hydrogen on the opposite end of the spectrum is going to be partially positively charged. Okay, so we use this arrow to basically show the movement of the electrons, or sorry, the directionality of that negative electronic charge. And so we land at something like this arrow showing this is the partial positive charge of that molecule, and I guess the point of that arrow shows the partial negative space or partial negative direction there. Okay, when the two atoms are identical, the electrons are shared equally. We saw that with F2. That's a non-polar molecule. When the atoms are different, and the atoms are shared unequally, that's considered a polar molecule. So HCl is considered a polar molecule. HF, like we saw on the previous slide, or LIF are all polar molecules. Now, in order to classify a molecule or classify a bond, we use this electronegativity table to ultimately do a fairly simple calculation. So in a pure covalent molecule or in a purely covalent bond, your change in electronegativity, your delta En, your difference of electronegativity between the two atoms that make up that bond is going to be 0. That means it is 100% shared evenly. Now, a polar covalent bond is going to be, or is going to have an electronegativity difference. So I'm not going to give you a precise number, because if you look in different resources, you're going to find different numbers. And so I don't really think that it's a good point to like hang your hat on, oh, it's got to be 2.5 or something like that. And instead, just keep this in mind as a polar covalent bond will have a delta En that's small to medium. So let's go ahead and just say that it's, well, a delta En is greater than 0, but less than 2.0. 2.0. Okay, now if you have an electronegativity that's particularly great, a delta En that is large, which is what you would find whenever you use a metal and a non-metal, well, that would be considered an ionic bond. So you could kind of think about it as this is a spectrum. So we've got something that's purely covalent all the way down to ionic. So again, 100% shared to effectively 0% shared. And what I'm talking about here is the electrons being either 100% shared or 0% shared. So you could say that a bond is so polar that it would be ionic, okay? So think about this almost as a gradient and as a spectrum. I think that's a helpful way of looking at this. Now we've got these three examples. We've got oxygen-oxygen, nitrogen-oxygen, carbon-oxygen. So we want to know which one is the most polar. And in order to do this, you have to have those electronegativity differences. And I will tell you that the oxygen has an electronegativity of 3.5. Nitrogen has an electronegativity of 3.0, and carbon has an electronegativity of 2.5. Okay, so what we're doing is we're calculating our delta En. Okay, so by giving you these numbers, and if you were to be confronted with this information on or a question like this on an exam or a quiz or something like that, I will give you the electronegativity values. Okay, so when we have oxygen and oxygen, so two oxygen atoms, what's our electronegativity difference? Well, it's 3.5 and 3.5. So our electronegativity difference for this delta En equals 0. So this is our least polar molecule. Now our delta En for nitrogen, well, this is going to be 3.5 minus 3.0. Keep in mind this is an absolute value, so our electronegativity difference is 0.5. Okay, so that's more polar than our oxygen-oxygen bond. And our last one is our carbon-oxygen. So that's 3.5 minus 2.5 equals 1.0. So our delta En is 1. So our most polar bond and our most polar molecule in this case is going to be that one, the CO. So to correctly answer this question, most polar is going to be C, CO. All right, well, I hope this is helpful. Thank you very much. Have a good afternoon.